In this video, I'm going to give you some tips for solving the ALEKS problem called using the Van 't Hoff equation to predict K at a different temperature. So this problem is pretty tricky. I flipped through about 30 different versions of it. I feel like I kind of saw the pattern with the ALEKS, all the different versions of this problem. Hopefully, I'm going to give you enough information to solve all of the variations of this problem that you come across. So this problem is going to start off by giving you a temperature and an equilibrium constant. It's going to give you some random facts about the reaction, which are going to be either mostly useless or entirely useless, and then it's going to ask you 3 different questions about the reaction. The first question that's asking you is, can you calculate Kc at a different temperature? So notice here for mine, I'm starting, or it's providing me with a value of Kc at negative 16.5, and it's asking me if I can figure it out at a different temperature. If we can calculate the equilibrium constant at a different temperature, we're going to do that using the Van 't Hoff equation. And the only way that you're going to be able to say yes to this, the only time your answer is going to be yes here, is if you know, so we'll say if you know the value of delta H for the reaction. In this Van 't Hoff equation, if we can use it, we're going to be using it to solve for K2. ALEKS does provide you with one value of the equilibrium constant. It also provides you with both temperatures. It provides you with the initial temperature that goes along with that initial Kc value. It's giving you your new temperature. R is a constant. So the only way that you're going to be able to use this equation right here is if you know K1, delta H, R, T1, and T2. And then you could use it to solve for K2. If you know delta H, then the answer to this question is yes. So how are you going to know whether or not you know delta H? If ALEKS is going to give you delta H, it's going to be in one of these facts about the reaction. It's going to say something about kilojoules per mole of heat either being absorbed or released. So you're going to have to take that information and interpret that as a delta H value. So for me, my delta H is 142. It says that it is being absorbed, which means that it is positive delta H. So absorbed means positive delta H. If it was saying it was released, that would be negative delta H, and those units are going to be kilojoules per mole. So since ALEKS did provide me with information for delta H, then yes, I am able to use the Van 't Hoff equation and calculate the new K2, and then all that I have left to do is actually carry that math out and put the answer down here. So down here it says if you don't have information about delta H, you're going to say no to this. You're not going to answer this second question, and then you're going to have to answer this question down below. And this is where I'm going to draw a sad face, because this question is going to be the one that's actually pretty tricky. I am going to talk about what to do if the answer to this is no, but before we get into that, let's just go ahead and plug stuff into this Van 't Hoff equation just so we can see how the math works for it. So I am just going to rewrite it down here. My natural log of K2, that's what I'm trying to figure out, over the initial value, or the K1 value, which is, for me, is 3.2 times 10 to the minus 5. And that is equal to my negative delta H of reaction. For me, the delta H of reaction is positive 142. So be careful with the signs here. This wants me to put in a negative of my delta H. If my delta H had been negative 142, then down here this would be positive 142. This delta H value needs to be in units of joules per mole, not kilojoules per mole. So hopefully you're comfortable with that conversion. Negative 142,000 joules per mole, and that is going to be, whoa, I definitely don't have enough room for that. Slide that over. That is going to be over the ideal gas constant, 8.3145 joules per mole Kelvin. The units of the constant are joules per mole. That's why we have to switch the units of delta H. And then we're going to do 1 over, be careful with the temperatures, so it's 1 over T2 first. That temperature needs to be in kelvins. 273.15 minus 39 is 234.15 minus, still need even more room, 1 over T1 in Kelvin. T1 is right there. 273.15 minus 16.5 is 2 56, 65. We just got a lot of math to do here. So I'm going to do everything on the right-hand side. Negative 142,000 divided by 8.3145. Hopefully I'm not hitting any buttons wrong here. Times 1 divided by 234.15 minus 1 divided by 256.65, and that gives me negative 6.394, totally unitless. I left the Kelvin off of these numbers right there. Totally unitless. Scoot this over here. So this is the natural log of K2 over 3.2 times 10 to the minus 5. So to solve for that natural log, what we're going to do is take the inverse of the natural log, which is the e function. On the left-hand side, that's just going to make that natural log function magically disappear. Over on the right-hand side, we're going to have e to the negative 6.394. And I'll go ahead and do that on my calculator. E to the answer, I get K2 over 3.2 times 10 to the minus 5 equals 0.00167. And then I'm just going to do some algebra to solve for K2. 3.2 times 10 to the minus 5 gives me K2 is equal to 5.35 times 10 to the minus 8. It's a unitless number. I don't know how many sig figs ALEKS wants, but we could take a look at that. Two significant figures. So that's going to be 5.3 times 10 to the negative 8. And honestly, as rough as that equation feels, that Van Hoff equation, as difficult as it feels, I honestly would prefer to say yes here and have to do the calculation. This is the part of the problem that I would like to not have to deal with if I don't have to. So if your answer to this question was no, and that would be, you would say no because you were not given any information about delta H. Then ALEKS is going to ask you, can you at least decide whether the equilibrium constant is going to be bigger or smaller at a different temperature? And every version of the problem that I saw, it was asking me to compare or to make a decision about whether or not I could predict the value of Kc at a different temperature. In order for you to be able to do that, you can only say yes to this. And again, for me, for my particular problem, if you can solve this, if you can come up with a number for question number 2, you're not going to be filling out this part of the problem at all. So you're only going to be doing this if you said no up here. Okay, so the only way you would be able to answer this question is if you knew that the reaction was endo versus exothermic. And the versions that I saw where this was the option that you had to take, it would say something about heat being absorbed or heat being released, but it wouldn't give you the numerical value of delta H. Because you weren't getting the numerical value, you would not be able to actually use the Van Hoff equation. You wouldn't be able to do any kind of calculation. So it's just going to say something about endothermic versus exothermic. If you have an endothermic reaction, that means that heat is required for the reaction. I want you to think about heat as if it is a reactant. Endothermic, again, means that heat is required. Heat is going into the chemical reaction. So heat is a reactant. This is equilibrium. I got to draw those equilibrium arrows. And think about it like heat plus the reactants makes the products. This is for endo. If you have an exothermic reaction, then in an exothermic reaction, the heat is being produced. So I want you to think about this as reactant in equilibrium with the products and heat. And so endothermic reaction, treat heat like a reactant. Exothermic reaction, treat heat like a product. This maybe is going to feel a little bit like Le Chatelier's principle. Okay, so now that you got this figured out, pay attention to the temperature change that ALEKS is asking you about, and you got to be a little bit careful if you're dealing with negative numbers here. So this particular version of the problem says, can you decide whether Kc at negative 39, so Kc at a low temperature, will be bigger or smaller than Kc at a high temperature? Kc at a high temperature versus a low temperature. So it's telling us if we're starting out with Kc at a relatively high temperature, what's going to happen if we decrease the temperature. I'm just going to rewrite that. What happens to the position of equilibrium, in my case, if temperature goes down? And this part of the problem is going to be really, really specific to the conditions that have been given to you in your version of the problem, because it might be asking you what happens if the temperature goes up. It really totally depends on the number that ALEKS gives you. And then the way that you answer it is going to absolutely depend on whether you're dealing with an exothermic or endothermic reaction. So I have, for this particular problem, I know that I have an endothermic reaction. ALEKS told me that my heat was being absorbed, so I know that I'm dealing with an endothermic reaction. If my temperature goes down, thinking about Le Chatelier's principle, the position of equilibrium is going to shift to the left to try to put that heat back, which means in my case, the value of Kc will be smaller. This is due to the position of equilibrium being shifted to the left. Kc would be bigger if the position of equilibrium shifts to the right. And again, the way that this part of the problem makes me really sad, because the way that you're going to answer this question is super specific to your exact situation. So for an endothermic reaction, if the heat is increasing or if the temperature is increasing, that would cause the position of equilibrium to shift to the right, and then you would say Kc is bigger. If you have an exothermic reaction and the temperature is going down, then the position of equilibrium will shift to the right and Kc will be bigger. If you have an exothermic reaction and temperature is going up, the position of equilibrium will shift to the left and Kc will be smaller. And the only time that you're going to get to say no to this problem is if you don't know if the reaction is exothermic or endothermic. Then you would have to say no. Now, the thing that kind of stresses me out about this ALEKS problem is that I can't guarantee that I saw every single version of the problem, and a lot of the versions of the ALEKS problems talk about gases, change in the moles of the gases. Some of them give you kPs instead of kCs. And side note, if you get a kC versus a kP, that's not going to change the way you do any of this kind of stuff at all. But there's a part of me that worries about perhaps you might come across a version of the problem where it is a gas phase problem, it is a Kp problem, and this part of the problem might have something to do with pressure changes, volume changes. I didn't see that at all in any of the versions of the problem that I looked with. But if you do end up in that weird situation, I really want you, for this part of the problem, I really want you to rely on Le Chatelier's principle, because this part of the problem is totally about Le Chatelier's principle. And so I showed you what to do using Le Chatelier's principle if you know if the reaction is exo or endo, and hopefully you can navigate it if it's a pressure change situation. Okay, so super good luck on this problem, because it is really, really tricky, but I know you can do it, and I'm hoping that all of the versions of the ALEKS problem that you get are ones where you can say yes to this question because you know the value of delta H, and then you can just calculate a number, and you don't have to think about this part at all.